Hi students, today we are going to discuss about very short answer questions, okay, of the chapter chemical bonding from Abhyasa Deepika. Okay, so in this, the first question is, why do bond energies are same if beryllium forms one covalent bond with the s orbital and other with p orbital to form BeCl2 molecule? Why do bond energies are same? Okay, in case of BeCl2, the question will be displayed on the screen. Why do bond energies are same if beryllium forms one covalent bond with s orbital and another with p orbital to form BeCl2 molecule? That is the question which was given in Abhyasa Deepika. The question will be displayed on the screen. Please see the question and the solution will be on the board. Now, BeCl2 means beryllium chloride. So, why the bond energies are same? Even the bond lengths are same for both the bonds. When beryllium having s orbital combines with the p orbital of same beryllium, okay, during the bond formation, BeCl2. So beryllium atomic number is 4. Its configuration is 1s2, 2s2. Now ground state configuration, ground state electronic configuration is, this is a 1s2 with 2 electrons, and here it is 2s2 with 2 electrons, and in p orbital 2px, 2py, 2pz, 2px0, 2py0, 2pz0. This is ground state electronic configuration. So during the bond formation, so the electron is supposed to be promoted. That is, we are going to write excited state electronic configuration of beryllium, and here it is 1s2 as it is with 2 electrons, and 2s2. In this, 1 electron promoted to the 2px level, 2px orbital, that is 2s2. Here 2s2 configuration electron is promoted. Here 1 electron is 2s1 configuration, and in this we are having is 2px, 2py, 2pz. Here 1 electron promoted to the 2px orbital. So here 1 electron, and here is 0, 0, here 2px1. So the s orbital of beryllium combines with the p orbital of beryllium itself. So the s orbital of beryllium with 1 electron, 2s1 orbital, combines with the 2px1 orbital of same beryllium. Okay, they are going to combine. sp hybridization is taking place here. So results in the s orbital 2s1, p orbital 2px1. So they both will combine together like this. Here the overlapping is like this. Hybridization process is taking place and results in the formation of sp hybridized orbital. Okay, both sp hybridized orbitals, 2 orbitals are there. Here is 1 plus 1. 1 s is there, 1 p is there. There is 1 plus 1 gives rise to how many? 2. That is 2 sp orbitals. Here 1 sp orbital, here 1 sp orbital. So 2 sp hybridized orbitals are formed. So before bond formation, both these orbitals, sp orbitals, are having the same energy, same shape, and same orientation is there. So this is having the same energy, same shape. Both are having same shape, same energy, same shape and energy, and even orientation. This is the main reason why this the question was asked. Why this? I will read out the question again. Why do bond energies are same if beryllium forms one covalent bond with s orbital and other with p orbital to form BeCl2 molecule? This is in case of beryllium. So we got beryllium. Then I will rub this. Then I will explain the next part of this particular beryllium chloride molecule. Okay. Now this beryllium with the sp hybridized orbitals will combine with the chlorines. Chlorine atomic number is 17. 2 chlorines are there in BeCl2 molecule. 2 chlorines are there. Chlorine atomic number is 17. Configuration is 1s2, 2s2, 2p6, 3s2, 3p5. Understood? Now here, last shell is third shell. Here it is 7 electrons. To become stable, it requires 1 more electron. Is going to share its electrons. So I will write that. So in this clearly, if I write, this is a 1s2, first chlorine, and here it is 2s2 with 2 electrons and 2p6. So in 2p we are having 3 degenerate orbitals are there, 2px, 2py, 2pz. Here 1 electron, 1 electron, Hund's rule. We are going to follow the Hund's rule. Next one is 3s2. 3s2, 2 electrons are there, and even we are having a 3px, 3py, 3pz. So 5 electrons are 1, 1, 1 according to Hund's rule, 1, 1. 3px2, 3py2, 3pz1. So this 3pz1 orbital is having unpaired electron. This orbital will participate in bond formation. So hence if I explain next part, the bond formation will be like this. Now 3pz orbital of first chlorine with unpaired electron. This is 3pz orbital of first chlorine with unpaired electron. And I already explained about Be, and Be is having a, so this is sp and here it is sp. And next chlorine, same chlorine, 2 chlorines are there. First chlorine is like this, second chlorine is also in the same way. Now we are having a 3pz1 orbital with 1 electron. Here electron is there. Now here sp electron. Now when you observe this particular overlapping, here the overlapping is end-on overlapping. So this is a chlorine, this is a chlorine, and exactly if I mention the orbital what it is, it means 3pz1. Here it is 3pz1. Now these two orbitals are in end-on overlapping. End-on overlapping of atomic orbitals results in the formation of sigma 1. This is sigma pz sp, or if you want clearly 3pz sp, sigma 3pz sp. Okay, so we can write simply pz sp, sigma pz sp. So here is beryllium. Now bond chlorine, understood? So both the bonds are having a same energy. Bond energies are same here. This bond is having the same energy as that of this one. Now if I talk about the bond energy of this particular thing, 217 kilojoule per mole. And here also same energy, 217 kilojoule per mole. Understood? So bond energies are same. So this is the explanation for your question which was given in Abhyas Deepika first question. So both are having a same sp hybridization, chlorine with the unpaired electron, one unpaired electron, and the bond is, okay, beryllium. The bond angle, if I want to mention, the bond angle is 180 degrees and shape is linear. Okay, so because of sp hybridization, both sp hybridized orbitals are participating in bond formation with 2 chlorines. So here sp orbital of first, beryllium with the first chlorine, here sp orbital with the second chlorine. So in both the cases you observe pz orbital, sp, pz orbital and sp orbital, hybridized orbital of beryllium. So hence because of that both are having the same bond length. Even if you want to write the bond length, you can write bond length and bond energies are same. Understood? So bond length and bond energies are same. That is bond length, if you want, 1.75 angstroms and 1.75 angstroms. So beryllium to chlorine bond energy is 217 kilojoule per mole, and beryllium to chlorine bond length is 1.75 angstrom. Understood? So this is the explanation for the first question. I hope everybody understood this. Write the bond angles of H2O, NH3, CH4, BeCl2 molecules. Please see the question on the screen. It is displayed on the screen. So write the bond angles of H2O molecule. Second question, bond angle of H2O molecule, NH3, CH4, and even we have is BeCl2. So I will write clearly about even not only bond angle, next one is hybridization. I am going to write everything, type of hybridization and even the shape. Okay, H2O molecule, bond angle is 104 degrees 31 minutes. Okay, next one is ammonia molecule, bond angle is 107 degrees 48 minutes. And next one is methane molecule is 109 degrees 28 minutes. And BeCl2, beryllium chloride, is 180 degree. And hybridization is, in H2O molecule, hybridization is sp3. In ammonia is also sp3, and in methane is also, that is sp3, and in BaCl2 hybridization is sp. Okay, if you wish me to write one more, that is I will write clearly about BF3. BF3 bond angle is 120 degree and hybridization is sp2. Because why I am writing all these means chance of getting questions in the bit part, not only in very short answer questions, even in the bit part also chance of getting these. And the shape of this molecule is V shape. According to 10th class textbook point of view, I am writing as a V shape. Okay, next one is ammonia. The shape is pyramidal, and methane is tetrahedral, and BaCl2 is linear, and BF3 is trigonal planar or plano triangular shaped molecule. Okay, so this is about water molecule, ammonia molecule, methane, beryllium chloride, BF3, bond angles and type of hybridizations and even the shapes. Very, very important. Now the next question is, why do bond angle of H2O molecule is 104 degrees 31 minutes? This is a very, very important applicative question. Why the bond angle of H2O molecule, why the bond angle of H2O molecule is 104 degrees 31 minutes? Sir, sp3 hybridization means bond angle is 109 degrees 28 minutes. Na? So even though water molecule has got sp3 hybridization, why the bond angle has reduced from 109 degrees 28 minutes to 104 degrees 31 minutes? Okay, this is a very, very important application based question. Reason is, now if I talk about the shape of water molecule, okay, so this is oxygen atom. Oxygen atomic number is 8, configuration is 2, 6. Last shell is having how many electrons? 6 electrons are there. To become stable, it requires 2 more electrons. So based on the concept of hybridization, we can explain this. Okay, now if I draw the structure for that, okay, now directly I will draw the structure here for this one. Now the type of hybridization is sp3. So the hybridization is sp3. Bond angle should be 100 degrees 28 minutes. Na? Why it is 104 degrees 31 minutes? The reason is presence of lone pairs. Okay, presence of lone pairs. According to the concept of valence electron pair repulsion theory, lone pair repulsion is more than lone pair bond pair repulsion. Lone pair bond pair repulsion is more than bond pair repulsion. In case of methane, no, we don't have any lone pairs. We have bond pairs. So in case of methane, we have 0 lone pair electrons. 4 bond pair are there. In case of NH3, we have 3 bond pair and 1 lone pair. And in case of water molecule, now if I draw the structure of that water molecule, here we have lone pair of electron, here is hydrogen atom and here is hydrogen. So this is one bond pair, this is one bond pair. So in case of water molecule, we have 1 plus 1, 2. 2 bond pairs are there. Whereas lone pairs are how many? 2 lone pairs. Okay. So 2 lone pair. As we know that the lone pair repulsion is more than lone pair bond pair. Lone pair bond pair repulsion is more than bond pair. So between these 2 bond pairs, very negligible repulsion forces are acting. So whereas between these 2 lone pairs, more repulsion is there. So because of the repulsive force between these 2 lone pairs, okay, the electrons move apart because of electrons are having same charge here. Okay, and the force is exerted on these particular bond pair. So hence because of that, Because of that, the bond will be pushed in downward direction because of the repulsive forces. These two bonds will come a little bit closer to each other. Actually, the bond angle should be same as that of methane, that is 109 degrees, 28 minutes. But because of the lone pair repulsion is more than bond pair. Even lone pair bond pair repulsion is more than bond pair. Hence, the bond angle will decrease from 109 degrees 28 minutes to 104 degree 31 minutes. Bond angle is. Now, if I write clearly, here the hydrogen, bond, here lone pair electrons. The bond angle is 104 degrees 31 minutes. That is the main reason. Okay, I hope you understood this explanation. Explain hybridization of orbitals. What is hybridization? The concept of hybridization was proposed by Linus Pauling. So what is hybridization? I will explain very clearly about it. Now the concept of hybridization was given by Linus Pauling. Linus Pauling proposed the concept of hybridization. So what is hybridization means? The process of intermixing up of atomic orbitals, different atomic orbitals. Okay, atomic orbitals result having different energy and shape and different orientations results in the formation of new hybridized orbital having same energy, shape and orientation. The process of intermixing up of atomic orbitals having different energy and shape with different orientation results in the formation of new hybridized orbitals having same energy, shape and orientation is called hybridization. The concept of hybridization was proposed by Linus Pauling. Pauling proposed the concept of hybridization. Is it clear? So Pauling has proposed the concept of hybridization. Now we are having a different type. Now what are the basic difference between atomic orbitals and hybridized orbitals means? Compared with atomic orbitals, hybridized orbitals are more stable. That is the main thing. More stable, gives more stability to the molecules when they participate in bond formation. Because of these hybridized orbitals, the molecules will get more stability. Okay, so we are having different depending upon the type of orbitals which are participating in concept of hybridization. So we have different type of hybridizations. In that we are having is sp hybridization, sp2 hybridization, sp3. In sp3 also we have different types are there. Okay, sp3d, sp3d2, sp3d3, which we are going to study in intermediate. Now, 10th class point of view, these three are very, very important. sp hybridization, sp2 hybridization, sp3. Okay, next question is, please see the question on the screen. Give examples of ionic compounds. The best examples for ionic compounds are NaCl, KCl, MgO, Al2O3, etc. Many are there. Okay. So NaCl, KCl, MgO, Al2O3, aluminum oxide, etc. Even you can go with the sodium oxide, Na2O, potassium oxide, K2O. So if you observe common thing in these ionic compound examples, sodium is a metal, chlorine is a non-metal. Potassium is a metal, chlorine is a non-metal. Magnesium is a metal, oxygen is a non-metal. Aluminum is a metal, oxygen is a non-metal. Sodium is a metal, oxygen is a non-metal. Potassium is a metal, oxygen is a non-metal. So we have several examples, but the most common examples which we used to come across according to textbook point of view, these are much important. Okay, these are the examples of ionic compounds. Next one is examples of covalent compounds. Next question is, that is sixth question. Sixth question is examples of covalent compounds. In this, examples are H2O, NH3, third one is CH4, fourth one is BF3, etc. Many are there. So these are general examples. Then you can write, if you want, you can write a BeCl2. Many are there. Okay. So these are the examples of covalent compounds. Seventh question is give examples of pyramidal shaped compounds. In that we have best example is NH3 means ammonia, PH3 nothing but a phosphine. This is ammonia. And one more example is H3O. H3O plus ion. This is a hydronium ion. So these are pyramidal shaped compounds. Now next question is what is the shape of H2O, NH3, CH4, BeCl2 molecule? Previously I already explained that particular question in the form of a table like thing, that is in this video only. Okay, that is for second question. Okay, so even though I will write again, what is the shape of H2O molecule? H2O molecule shape is V shape. The question number is 8th one. H2O molecule shape is V shape or bent or non-linear, some other books, but according to your textbook point of view, you should write V shape. Next one is shape of NH3, ammonia. And next one is CH4. Next one is BeCl2. NH3 is pyramidal. And methane is tetrahedral. And BaCl2 is linear. And if you want, you can write how many number of lone pairs are there, how many bond pairs are there. So in a water molecule, 2 bond pairs, 2 lone pairs. In ammonia, we have is 3 bond pairs, 1 lone pair. In case of methane, that is 4 bond pairs, no lone pairs. In case of BeCl2, 2 bond pairs, 0, that is no lone pair. Okay, important. Next, 9th question is draw the shapes of H2O, NH3. Next one is CH4 and BeCl2 molecules. Based on the concept of hybridization. Based on the concept of hybridization. This is CH4. Here, clearly, if you wish me to write, this is S orbital, this is sp3, and non overlapping. Now, clearly, you write this is the way. And you can mention clearly this is 109 degrees, 28 minutes bond angle in a, that is a methane, and shape is tetrahedral. If you observe here, the bond pairs are 4 bond pairs, 0 lone pairs. Okay, this is about a methane. Next one is, I hope you understood this. If you want clearly, I will mention this also. This is a sigma S sp3, sigma S sp3, sigma S sp3, sigma S sp3. Okay, how many sigma bonds are there? 4 sigma bonds, no pi bonds. Remember that. Okay, this one is NH3. S orbital, S orbital, hydrogen. Here, no, here lone pair, hydrogen. Okay, so here lone pair. Now here sigma S sp3, sigma S sp3 and are overlapping, sigma S sp3. Now very short form if I write clear structure like this. And in this case if you observe, one lone pair is there. How many number of lone pairs? One lone pair. 3 bond pairs. And how many sigma bonds are there? Sigma bond, sigma bond, sigma bond. 3 sigma bonds. And no pi bonds. And bond angle, I already mentioned in the previous questions. The bond angle has decreased from, even though it is having sp3 hybridization, the bond angle has decreased from 109 degrees 28 minutes to 107 degrees 48 minutes because lone pair bond pair repulsion. Bond pair repulsion is very negligible, least compared with the lone pair bond pair repulsion. So because of these repulsive forces between lone pair and bond pair, the bond angle has decreased from 109 degrees 28 minutes to 107 degree 48 minutes, and the shape is, this is the shape is pyramidal. Already one question was given the answer, that is examples for pyramidal shaped molecules. Okay, and next one is water molecule. So in this case, water molecule, we are having a s orbital. Here this is hydrogen atom, s orbital, and hybridization sp3, 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 sp3. Okay, here two lone pairs are there. Here one bond pair, sigma S sp3, sigma S sp3. So as two lone pairs are there. Now if I write clearly, this is oxygen atom, hydrogens, and this is oxygen atom. Okay, so oxygen here lone pair, and here hydrogen, bond pair. No. Bond angle is 104 degrees 31 minutes, and shape is V shape. Bond angle is 104 degrees 31 minutes, shape is V shape, and the number of bond pairs, 2 bond pairs, 2 lone pairs. Sigma is sp3, sigma is sp3. How many sigma bonds are there? 2 sigma bonds, 0 pi bonds. Shape is V shape. Bond angle is 104 degrees 31 minutes. Okay, next is BeCl2. Beryllium sp hybridization. So we are not showing the hybridization process. Just we are writing, he asked to draw the shapes only. So here Now this is a chlorine and this is a chlorine. Here this is a beryllium. And iodation is sp. Now sp we have here is sp. And this is a pz orbital. That is a 3pz orbital. That is a, this is a pz. Clearly if you want to connect 3pz, and here it is 3pz orbital of second chlorine. So the overlapping is end on here. End on overlapping sigma bond. pz sp. pz sp. If you want to place sigma pz sp, otherwise sigma 3pz sp, 3pz sp. Now if I write clearly Be Cl Cl. This is one sigma bond, sigma bond, sigma bond, sigma bond, sigma bond, sigma bond. Bond angle is 109 degrees. Sorry, 180 degrees. Bond angle is 180 degree. Shape is linear. And bond pairs are 2. Lone pairs are 0. And shape is linear, bond angle is 180 degree. Okay. Now the 10th question is, question will be displayed on the screen. Represent each of the following using Lewis notation. He has given notations, Lewis notations for element calcium, Br2, and carbon dioxide CO2, and even beryllium. So we have to represent them. So for this case, calcium, we know calcium atomic number is 20. If you write clearly the configuration 2, 8, 8, 2. Last alumini only 2 electrons. So those 2 electrons we have to show calcium with 2 electrons. We can show here dot picture like this, otherwise calcium. Okay, next one. Br2. Bromine, atomic number is, do you know atomic number? Okay, fluorine is 9, chlorine is 17, and bromine is 35 atomic number. So last shell, bromine has got 7 electrons. So we are going to show bromine molecule. So here 1 electron, here 2, here 2, here 2. And Br, here 2, last shell 7 electrons. So this is dot picture of bromine molecule. Bromine. Okay. So Br, bromine atomic number is 35. Configuration 2, 8, 8, 2, 18, 7. So if you count all these, 18 plus, that is 18, 26, 28, 35. Okay. 2, 8, 18, 7. 8, 26, 28, 28 plus 7, 35. So this is a bromine molecule. Next one is carbon dioxide, dot picture. Carbon. Okay, dot picture. Carbon, last shell, carbon atomic number is 6. Last shell, first shell 2 electrons, last shell 4 electrons. So carbon, here I will draw 2 electrons, here 2 electrons, dot pictures, only simple adding dot pictures. And this is in case of CO2, dot picture. Okay, dot picture of CO2 molecule. Clearly, if you show bonding, like this is. Okay, next one is beryllium. Beryllium atomic number is 4. So last shell has got only 2 electrons. Beryllium with 2 electrons. We can show like this. Otherwise, okay. So this is these are the dot pictures of beryllium, carbon dioxide, Br2, and a calcium. Okay. So I hope you all understood these 10 questions which I explained. These questions are from Abhyasa Deepika, and these all are very, very important even for the coming revision or practice tests, okay, which are going to be occur. Okay. So I hope everybody understood all these questions, explanation. And if you have any doubts, and please comment in the comment section, like, share, and subscribe and support me. Thank you.